I don't really feel out of place coming at this point in the meeting, even though I represent the numerics track, because we interface in the algorithms community with almost all the other aspects of the workshop. Whether it's architecture, applications, algorithms, programming models, or system software, as you know, these now form an interconnected ecosystem. The hallowed idea of separation of concerns from Dijkstra is harder and harder to preserve when there are so many optimizations that can be obtained by looking over the transom to the other disciplines. And algorithms and software, of course, in the middle. Right now, they span two diverging communities, the architecture, which wants us to become more uniform at the fine scale for energy efficiency, and the algorithms, which want us to be more adaptive and non-uniform, multi-physics, multi-scale, et cetera. So I would connect, I think, partly to Rick Stevens' dinner talk last night on convergence of big data and extreme computing, to the architecture presentations that you've heard yesterday or coming up, to the programming model presentations, including some today and some to come. I think you'll hear about all of these different programming models this week from, in many cases, their own designers, like Carter Edwards with Cocos, and I think Warburton with Oka, and so forth. And of course, to the main people in track 4, who will mostly appear a week from Monday, the fast math team of SIDAC, the seed team of the ECP, and Almgren, Demmel, and Don Guerra. My theme is this one from Wayne Gretzky. A good player plays to where the puck is, while a great player skates to where the puck is going to be. And the idea is, can we design algorithms for where architectures are going to be? Can we, in fact, emulate the prescient wisdom of the MPI designers, but with a much larger space? So the outline of my talk will be to very briefly discuss the boundary conditions under which we operate, the architectural and application trends that the algorithms have to span, and focus on the limitations of our current software infrastructure for exascale, which will mainly be our high sensitivity to synchronization. And then talk on a group of four algorithmic imperatives that are certainly necessary for extreme scale, but will almost all help in a good way today. 4 sets of, if you will, bad news, good news about the way architectures must evolve. 4 widely applicable strategies. I bet you'll find something you're thinking about in those 4. And just then to illustrate some sample points of light, if you will, not full solutions, but steps along the path coming from my own group at KAUST. So architectural trends. You know these. The clock rates no longer are increasing, while arithmetic capability continues to increase through massive concurrency. Memory storage capacity does increase with each generation, but doesn't keep up with the capacity per core. Transmission capability, similarly, we do get better and better engineering there, but not as fast as the cores are increasing in most contemporary chips. And with the complexity and size of the system, the mean time between hardware errors shortens, and maybe that has some implications for the amount of error correction that the software and even the user software should begin to absorb in order to get the best performance efficiency, knowing the kinds of errors and their severity. So billions of dollars, or whatever your favorite unit, of open source, community-based scientific software, not to mention the commercial stuff, hangs in the balance if we're going to make good use of the kinds of machines that Paul Messina and company are going to provide for us. Several years ago, there was an attempt to write a roadmap whereby the international community, specifically agencies from the G8 countries, could coordinate this massive migration of these important open source codes in science and engineering to the exascale. I think 11 of the authors that you see here in very fine print are speaking to you this week. So in many ways, they recognized things that are coming. And I take from that in my talk just a few architectural boundary conditions. We need to get to approximately 50 gigaflops per watt. That is based on the exascale at 20 megawatts. Today, we're typically around 5 gigaflops per watt for a fully loaded system, a little bit better without the memory and the networks, of course. But that's a big order of magnitude in efficiency to go along with the order of magnitude in absolute aggregate performance that we need to achieve in just a few years. Because of the complexity of these systems, processor clocks may not be uniform. They may be scheduled by their own learning or by programmer knowledge to speed or slow in different phases with different requirements for maximum energy efficiency, or they may be dynamically imposed without programmer permission, if you will, from power capping or thermal monitoring. And this makes per node performance unreliable, no matter how great a load balancer you are. And the reduction required in power per flop in order to achieve these new levels of efficiency and per byte stored and moved may make computing and moving data less reliable. No one likes to talk about that, but I think as performance engineers, we should talk about that in order to show the designers what they can do, what we can clean up after them for. Circuit elements will be smaller, subject to greater noise. There'll be less space redundancy or time redundancy. Most error correction requires voting in space or redoing in time. And if we can knowledgeably deal with some of those, we can improve the path towards energy efficiency. This data is actually old, I say today, but John Schalf recently told me that it's actually not far from today. You can see the 2 order of magnitude difference between doing a double precision floating point multiply add at about 100 picojoules and moving one of those double precision words across the whole system with different levels of energy required in between. A pico, 10 to the minus 12 of anything done in exa, it works out to a mega, of course, per second. So 100 picojoules at 1 exaflops for the arithmetic only is 100 megawatts. That's not affordable. A megawatt year is $1 million. We use 1.4 kilowatts continuously as OECD people. So that's 71,000 people's worth of electricity. Exa is different. We've had this very heady improvement of a factor of 1,000 in performance every 10 years since the first Gordon Bell Prize, factor of almost 1,000 every 10 years in terms of power efficiency, but those things were riding exponentials that may no longer apply. In particular, Dennard's law has already ended. Dennard was the one who said if you dope it more by a factor of kappa, you can reduce the linear dimensions by a factor of kappa, the area dimensions by kappa squared, and for the same unit of power per square centimeter, you can get kappa squared times more computing, but that didn't take into account the copper. Of course, when you shrink that, you begin to be limited by resistivity losses and heating and so forth, and these colliding lines have been forecast for many decades, and finally they're upon us. Now, last night Rick Stevens showed you this wonderful canonical abstract node from a future exascale machine showing a lot of hierarchy, a lot of thin, very inefficient, energy efficient cores that have a lot of thread uniformity, one instruction, hundreds of executions, versus the fat cores where you do prefetching and out-of-order execution, and you make an individual thread very fast. And then there's the heterogeneity in the memory, a low capacity with very high bandwidth, high capacity with lower bandwidth, and maybe now 3 or 4 levels of memory technology within a node or right next to it. So there are these architectural resources to balance that an algorithms designer cannot be blind to, and the granularities and the nestednesses of these hierarchies. There's the heterogeneity of the processing elements, the memory, the intra-node network, because if you have 256 processors within a single node, there's a network that affects them and their paths to the memory at the perimeter. And then the inter-node network that Bill was just talking about, for example, in terms of topology, and that he started the very morning with the colliding NICs and all the DAGs in the time per different message size graphs. And now that you've seen some of the wisdom behind understanding those curves, you can understand that they are replicated even within a node. So for performance tuning, which of these resources is limiting as a function of time? Let's not score ourselves by always saying what percentage of flops we're getting if we actually are using all of the available memory bandwidth. And the performance seeker must be first aware of what is limiting and work up against that boundary. Well, there are well-established trade-offs for dealing with these architectural problems. In some cases, decade or so old when these began to be seen. There's the whole area of communication avoiding algorithms that Jim Demmel will speak about midweek, how you can exploit extra memory that happens to be available on a node to, in very common cases like matrix manipulations and grid stencil evaluations, achieve an actual theoretical lower bound on communication volume. It turns out that most of the LAPAC and ScaleAPAC routines have not traditionally been close to their theoretical lower communication bounds, but now we know what those bounds are, and now versions of those are being written. There are synchronization avoiding algorithms. Here I would actually call attention to some of Bill's work on Krylov methods, grouping the global inner products of each Krylov vector in an orthogonalization or conjugacy step to have fewer of those communications which have more data in each one, and then more flops to unwind the data, because you didn't orthogonalize one by one in the best mathematical order, but you saved some synchronizations. And there's been a lot of work in that as well. And then higher order discretizations, which really we've known were important in terms of saving memory for a given accuracy going back to the 1970s, when CFD people were saying, what's all this second order stuff? We should at least be at fourth order. Well, I'll show you a little graph later about 32nd order in a CFD computation and how that's the most energy efficient way to use a couple of major supercomputers like Blue Gene and Cray XC40. But we can perform more flops per degree of freedom loaded into high levels of memory close to the processor, just a cycle away, not having to pay back and forth to memory with a much larger data set from a lower order discretization. So going back to some of the basic numerics can actually help deal with some of the architectural constraints. Of course, not everything fits. If you have shocks, you won't be able to maybe exploit this, but it just shows the variety of adaptations that algorithms people may want to make. I would claim going forward that node-based weak scaling, like we've been doing in Gordon Bell for 30 years, is routine, but thread-based strong scaling is hard, and it is the game. If you think of an exascale configuration as a 1,000,000-way 1 gigahertz node, so that's 10 to the 6th, 10 to the 3rd, 10 to the 9th, as your 10 to the 18th, it wouldn't be hard to expand the number of processor memory units beyond 1 million or so. Yeah, you pay a logarithm, but we get all the memory bandwidth and the memory with it, as long as the nodes are performance reliable, so that synchronization doesn't hurt us at that scale. But the real challenge is usefully expanding the number of cores within a node to 1,000 or so. It's already 256 threads for KNL, depending on how you count threads, maybe more for GPUs. And all this must be done while the memory and memory bandwidth aren't layered on in proportion. And for those of you who are saying, I can't wait to get to an exascale system, well, we have the hard parts already today in the individual nodes. So the familiar is not so hard. Here's machine number 1. There's our machine at KAUST in the upper right-hand corner. Sequoia, K, some of the traditional top 20 machines. But the hard part is all this new stuff within a node, the ARM chip, the NVIDIA P100, the Power 8, the Intel Knights Landing, and their forecast successors. And this is a little sketch of Knights Landing, just to remind you of the hierarchy within a node of different cores, each of which has their own cache hierarchy. Some caches are shared between cores. There's a communication network between those. They go to different kinds of memory at the perimeter and so forth. You can start playing with exascale systems by learning how to get close to linear strong scaling on nodes like this today. Just to remind you of the inspiring accomplishments of your predecessors, this was the first terascale machine, ASCII read at Sandia. I sometimes joke it was the last balanced machine. It was a teraflops. It took nearly a megawatt. Now you get the same floating point performance of a teraflops for about 3.5 less orders of magnitude with, for example, the new ARM chip. Those two are in this table. You can see some of their comparisons. Let's add a few more interesting bits of hardware to this table and look at the right-hand column, the power efficiency in terms of gigaflops per watt. The exascale system at the bottom, which isn't delivered yet, will require somewhere around 50. We're actually not that far from it with Taihu Lite, which is a full system, including the memory and the network, but very, very austere programming environment, no cache. It'll take a lot of productivity to make good use of that machine. The Knights Landing and the NVIDIA are shown without the burden of their network and larger memory and so forth. They're getting very close to the power efficiencies that we need. But how are most scientific simulations implemented at the petascale today? Well, we do iterative methods based on data decomposition and bulk synchronous exchange, typically, of data. We distribute every large data structure. We work on a subdomain owner computes. We exchange lower dimensional, hopefully, information at the boundaries, surfaces exchange to compute on volumes. And we balance both the computation and the neighbor communication and find parallel paths for both. And if we can do that, we can defeat Amdahl and go to arbitrarily large weak scaling. And this programming model is bulk synchronous or single program multiple data or communicating sequential processes. 3 decades of stability, lots of good infrastructure. MPI doesn't require this, by the way. It's more versatile, but it's usually used in a bulk synchronous way. The name, in fact, comes from a famous paper by a Turing Award winner, Les Valiant, who argued just as von Neumann architecture is easy for architects to target and programmers to code to, the bulk synchronous model is an easy model for architects to build to and parallel programmers to code to. But you could ask, is that the best way to use an expensive network? To have it sitting idle almost all of the time, and then to have it all burst, from every processor in one big synchronous exchange? That's never been, a good engineering solution, if you will, for a very expensive piece of the supercomputer, although it was very good for productivity. Well, maybe we have to think a little bit beyond that. Here's your classical domain decomposition, could be particle decomposition, agent decomposition, or whatever. We want to do a large amount of work locally, and then at regular intervals communicate a lower dimensional amount of data. And following this paradigm, we've been able to achieve in real scientific codes, petroleum reservoirs, mechanics, gravitation, materials, quantum chemistry, a factor of 1,000 every decade, as mentioned earlier, and nearly a factor of 1,000 in price performance per installed gigaflops on real applications. This has been possible within the same programming model and the same understanding of who takes care of what. The hardware and the system software handles the errors, for example. And the user takes care of typically the mapping and takes care of the MPI communication. Same classes of algorithms. But scientific computing is now at a crossroads as we face the less performant, reliable, very high granular exascale future. Well, it looks different and maybe difficult, but we once said that about message passing. Bill and I are old enough to remember when people complained, what, you expect me to write that part of the operating system? I think that this is not something to be avoided and left to somebody else. I think this is where the fun is and where the good theses are and so forth in colonizing exascale, to have the algorithm community see the difficulties and go along for that ride. Now, almost all good algorithms that we know in linear algebra, by good I mean like n log n or somewhere near optimal, they require regular synchronization. We like to do inner products across a global state. We like to take norms to measure convergence. We like to pivot globally for best stability. We like to take fresh residuals. And we like them to be true at a given time frame before we move on to the next one. And this already tends to hurt efficiency. It can be fragile even for smaller concurrency if you have adaptivity, like some atmospheric model where the chemistry is active in one half of the world where the sun is shining and not otherwise. But concurrency is heading well beyond into the billions of cores, and so giving up synchrony is probably an important objective. So from the bulk synchronous generation, here's the baton for the energy-aware generation. The same group, more or less, that was working on the International Exascale Software Project has now been looking at the convergence of big data with extreme simulation. And there is a draft report available at this URL, exascale.org, for this merger. It's actually rather incomplete, but it's expected to be ready by supercomputing this year. So it's a successor to the software project roadmap. And what you will find is, as Rick previewed for you last evening, there are essentially different worlds running different software stacks in different hardware environments, looking at different applications that don't talk much to each other, but both are hitting some hardware limits. and both could benefit in their own core mission by working more closely with the other tracks. I'm not going to belabor this slide, which you can find in Communications of the ACM along with the corresponding article of a couple of summers ago. But MPI and Linux are about the only thing in common between these two software stacks. One of the things you will find in this report is this little 3x3 matrix showing the relative contributions and dependencies that large-scale simulation, big data analytics, and machine learning, three separate technologies, all anticipating exascale, how they will interact, really. So for simulation, analytics can provide steering in high-dimensional parameter space. We may need to do a lot of runs, but we may not need to tile the space. And we can do a lot of in-situ processing, which can save I/O. Learning provides smart data compression, and as Rick actually featured last night, maybe even replacement of first principles models that may not be that good with learned functions, such as cloud albedo or something like that. Simulation can provide to analytics some kind of physics-based regularization. Analytics will give you some answer with a high probability, but some of the answers that have equally good probability may violate energy conservation or some other physical principle, which a simulation could regularize. That's, I think, a term that Vipin Kumar's group has been using at Minnesota. Also, sometimes big data isn't that big, and simulation can provide first principles data for training, for augmenting real-world data. And I won't go so much into the interaction of the two fields of big data with each other, but learning can provide to analytics some imputation of missing data and some detection and classification, and analytics can provide extra feature vectors for training. So it's good that we actually build algorithmic tools that allow a simulation to run in situ with the machine learning application, so we're not moving huge data sets on and off disks. And the more that we can bring these two communities together in the software environment and the hardware environment in which they run, they will have these benefits. So I said there were 4 groups of 4. What are the 4 algorithmic imperatives? Well, I hope I've argued that we need to reduce synchrony. Bill has been, and the MPI guys have been arguing that all day as well, either in frequency, how often we synchronize, or how globally we synchronize. It may be okay to synchronize often within a chip, but not across a basketball-sized court of racks. We want to reside high on the memory hierarchy. Another way of stating this is that we want to have good arithmetic intensity. We want to have a lot of flops per byte loaded into the upper level of cache. Because of the nature of the high-performing cores, we need to increase the single-threaded or single instruction style concurrency. We need to have some small blocks that are highly uniform that can be batched across a large number of threads. And ultimately, we want to be able to build in resilience. I won't have much to say about the 4th topic here, because my own work hasn't addressed it much, but there's been a lot going on in linear algebra since the beginning of linear algebra, really, on this kind of topic, and especially recently, and more in other subjects as well. 4 bits of bad news and good news. We must explicitly control more of the data motion. That's simple engineering. That's where the cost is in time and energy. So we want to control that. And we'll get opportunities to control the vertical part of that. We've been controlling the horizontal part through MPI, but the vertical replication into caches and registers was not often available to us. Yes, we can specify some prefetching or things that can or cannot be aliased, and we've been able to roll things in and out of GPUs, but we may have many layers of memory hierarchy in the data typing even that will give us more control here. The use of high precision in nodal bases on dense grids, what a luxury that has been costing us a lot of energy and memory. A smooth function shouldn't need a 64-bit word at every point on a very fine grid in order to represent it. We know better mathematically, using continuity, using hierarchical bases, using sparse grids. We can store the same information to the same accuracy with many fewer bits. And we also don't need to communicate all those high precision words. If you monitor a single message that goes back and forth in an iteration of some typical scientific code, where the fields are continuous in space and time, it may only be changing in the lower bits. This is something that we could optimize for in just communicating the deltas. Iterative correction in linear algebra is a classic method of storing a small amount, a lower dimensional part of the problem in double precision and doing the update work in single precision on the lower part of the mantissa. And we'll think more and more that way. Equidistributing errors to minimize resource use. The requirement of doing that to understand where the errors are and not over-resolving some phase of the computation will lead to really fun numerical analysis. We are used to fully deterministic algorithms, but they may be too synchronization vulnerable. Rather than wait for missing data, we may be able to predict it using, for example, machine learning and continue. After all, machine learning is used for things that are far less predictable than the continuum equations. We do this with increasing success in problems without models. It should be fruitful in problems that have models. And of course, we can roll back if we made a mistake, but we can do the right thing most of the time. And again, there'll probably be a rich merger of classical numerical analysis with statistics to enable moving forward in this way. Fully hardware reliable executions may come to be regarded as too costly. Hence the algorithmic-based fault tolerance, which can relieve some of the constraints on hardware and on the operating system. Developers may, for their own advantage, partition their data and their programs into two sets, those that have to be executed reliably, like today, for example, to compute the residual, and to write it into a safe place in memory with error-correcting memory, and a larger set that can be done fast, less reliably, knowing that the errors will be catchable or their effects rigorously bounded. And there are many examples in direct and iterative linear algebra, LU, factorization, multigrid, and so forth, where most of the operations can be done in a less reliable way and still get a reliable answer. And von Neumann did not have reliable computers back in 1956, and this is a famous paper on cellular automata, and we need to write some more of those papers now. So the philosophy of an algorithmist is that we have to span a widening gulf between all these ambitious applications that probably about half of you in the room represent, and the austere architectures that the vendors standing up here are trying to pitch for you. And there are some few of us in the middle trying to do these adaptive algorithms. And this is a full employment program, by the way. This is not something to be sniffed at. What will exascale algorithms look like? I would argue that we should look no further than algorithms that are asymptotically of optimal order, namely O of n polylog n. Why? Because processor memory nodes tend to come with fixed proportions of processors in memory. And if when you grow your problem in memory, the work grows superlinearly in the amount of memory, you're not going to scale well at extreme scale. There are many optimal algorithms. They all tend to be hierarchical. Every decade has produced a notable one with a lot of variations and generalizations. There was the FFT, changing an order n squared algorithm to order n log n. Multigrid, similarly linear in the number of degrees of freedom to get to an answer accurate to the truncation error of the underlying local discretization. Fast multipole, doing the n squared potential interactions in time O of n. Sparse grids, representing a high dimensional problem, say n to the d, in n log n to the d minus 1, knocking out several powers of n without compromise in accuracy, taking advantage of continuity. H matrices, noting that even though we have the curse of dimensionality, we have the blessing of low rank, that a lot of operators in integral and differential equations actually can be represented in much more efficient bases. And recently, randomized algorithms that are actually getting rid of maybe even n's down to constants in some applications which are suitable. Like you want to take an FFT of a signal with actually a low number of sinusoids, and you might get it in less than order n. And with great computational power, namely big N, comes the responsibility to get to know and to use and to adapt and to generalize more of these methods. In fact, you could say that H matrices are a generalization of fast multipole to operators that don't have a known Green's function. Fast multipole is sort of like a matrix-free version of hierarchical matrices if you do have constant coefficients. This is the software that needs to be moved to exascale. This is just a subset of it, of course, but we could think of it in at least 3 categories. That's related to the modeling that we do, turning the problem into an arithmetic problem for the computer and bounding the errors in it and setting it up effectively and doing its load balancing and so forth. All these things in the model related. Then the development related, how do you debug a code on 1 billion cores? There's not 1 billion pixels on your screen. How do you then put such a code into production mode on such a complex system? Very little of this comes from the vendors. Most of it is generated, frankly, by DOE and INRIA and places like that. And it has to be scaled up. I have a tiny little niche, and I hope that the rest of the things on this page are represented by many other people in the room. So I'm at the midpoint, and I want to recap the algorithmic agenda that we have. We have to reduce synchronization and communication, make it less frequent or less global. We need to reside as high as possible on the memory hierarchy, greater arithmetic intensity, most operations that we need just 1 cycle away from the processor. We need greater code uniformity to take advantage of the high concurrency in very austere processor units, accelerators, and algorithmic resilience. We need to quantify trades between the limiting resources, I should say. And then, why go to exascale in the first place? It's because today's grand challenge problems are supposed to be the inner loops of the real science. You run a forward problem, and instead of gasping over the finish line, you're going to run it 100 more times to optimize parameters, to do data assimilation, to quantify uncertainty, and so forth. So there are 4 widely applicable strategies that have been already put into use and will be talked about many times during the next 2 weeks by people standing where I am now. One common one, but one very important one, is to move away from bulk synchrony to dynamic runtime systems that respect the order of computation, but don't over-order the algorithm in terms of nested loops and subroutine boundaries. These are some of the systems. I listed them in alphabetical order to avoid politics. I think about 5 or 6 of them will be presented to you this week. We need to exploit data sparsity of the hierarchical low rank type to, again, meet the curse of dimensionality with the blessing of low rank in many of our operators. We need to employ high order discretizations. And we need to code to the architecture but present an abstract API so that most people don't have to code to the architecture but find the right level to live above it and then make the optimizations below that level, sort of the hourglass model of software. So let me talk about a few of these things and then give a few examples before Cleve takes over at dinner. So directed acyclic graphs. These can remove artifactual synchronizations in the form of subroutine boundaries and pre-scheduled loops. Bill talked about pre-scheduled communication loops, but there's even more pre-scheduling in the arithmetic loops. This exposes more concurrency. There is, of course, a disadvantage. If you make it too fine scale, you'll pay a huge cost managing what is, in effect, a large distributed data structure of its own, a task graph. And if you try to fully optimize concurrency, you'll lose some memory locality. So there's an important negative side here that is that it needs to be explored much more carefully than so far in many of these research projects. But here's an example of just to whet your appetite and remind you, and I'm sure Jack Dongaro will show many examples of this type since his group at ICL has pioneered it within linear algebra. But here is a generalized eigenproblem. You can think Schrodinger. A and B are Hermitian. You factorize B and apply its inverses to the left-hand side to get a normal eigenproblem. Then you do triangle reduction QR iteration. The first 3 steps are flop intensive. And for a little 4x4 matrix, they look like this, where flow is from top to bottom in time and concurrency is the width. So that Potereff-Cholesky factorization is in red, for example. And if you just did this in 3 subroutine calls, you'd have to stack these up. But if you followed the actual data dependency, you could merge them across subroutine boundaries, and in fact, you could even start, iteration of loop 2 before loop 1 was finished, if it was a complex set of operations. And here the arrows, of course, are the dependencies, and the critical path is the overall height. Wide is good, more concurrency. This is an example of using this in an application with the European Extremely Large Telescope, where there are 10,000 mirrors to be adjusted in real time to correct for atmospheric aberrations based on some lasers that the telescope will shoot out and get reflections from. And this is a large Cholesky solved for a covariance matrix. And if you just look at a little blow up here, you'll see different symbols representing different iterations. If this was a sequential computation, we would not have this concurrency available. What about hierarchical low rank? The advantage here is to shrink memory footprints of the discretizations of common operators so that we get quicker access to them, reduce operation counts at the same time, tune work to accuracy requirements. You can go from very small rank up to full rank. If you really need full rank, you go back to your default algorithm. But chances are, if you know the accuracy that your computation needs downstream, you can save here. And maybe turn what was a solver into a preconditioner even by going very low rank. The disadvantage, of course, to get into this transform space, you pay a compression cost, and not all operators compress well, and the best ordering for compressing an operator may not be obvious. There are issues here just like with sparse factorizations. The key tool is hierarchical matrices, which were proposed by Huckbush, same guy who proposed multigrid a few decades earlier, back in 1999, observing that off-diagonal blocks of typical operators have low effective rank. The overall operator has full rank, of course. It's invertible, has a high condition number, but it's full rank. But the off-diagonal blocks have very low rank sometimes. And by exploiting that representation of the off-diagonal couplings, memory requirements and operation counts approach optimal in the overall dimension n down the diagonal. They're polynomial in the rank of the blocks and ln log in n. And of course, constants carry the day. There are many trade-offs here. You can have a few blocks of larger rank, that's known as weak admissibility, or more blocks of smaller rank, that's known as strong admissibility. I think I have a picture, but first let me remind you how common low rank is. Here's the 1D Laplacian. Of course, it has full rank. It's invertible, but this block has rank 1 all the way to the diagonal. So does the inverse. That's the good news, that the rank of the forward and the rank of the inverse are the same, even though the inverse is dense. And you can compress such a matrix by recursively subdividing it and asking, is my next smaller piece amenable to, for instance, a singular value decomposition with a small number of non-zero singular values? And you keep subdividing the off-diagonal blocks until you find those that are small enough to make an SVD worthwhile. And then the overall representation is the sum of the green and the red blocks at different scales that remain. The red, in this case, would remain full rank. And these are pictures from Huckbush showing the strong admissibility, where all of these blocks, as they approach the diagonal, might have a common rank, whereas in the weak admissibility case, this big block might have a larger rank than this one. But still, there's significant savings there. So we shrink the memory footprints. Higher in the memory hierarchy means shorter latency. We improve the arithmetic intensity. We reduce the operation counts. The disadvantages are that high-order operators may be less suited to some solvers. For instance, we've experienced that Hermite discretizations where you have both values and derivatives can't be compressed very well compared to discretizations where you just have all grid values. These the classic good solvers like algebraic multigrid may be less amenable here too. But actually, recently, Hesthoven and colleagues have been showing very good compressibility for HP finite element methods. What about high-order discretization? This is just a slide. It's too much detail, but I didn't have time to strip it down. What you see going across the x-axis here is the order of a spectral element in a CFD code from 4th order to 32nd order. Just follow the blue bars of the histogram. That's the performance of the best method for Intel's libx SMM on a Cray XC40, and the gigaflops are referred to the scale at the left, and you see by going from 4th order to the 32nd order, an improvement of a factor of about 4 or 5 in the performance of the chip in gigaflops. The bandwidth, the use of the bandwidth is shown in the continuous curve. Again, the purple one for the best of these 4 different linear algebra libraries. This is all for doing the Helmholtz solve in a spectral element code. You could ask, okay, rate is one thing. What about time to solution? That's the more important metric. Here you see a measure of accuracy, and here a cost in core hours. And here you see the order of the element and the number of elements in each linear dimension versus a higher order and a smaller number of elements. And so for the same accuracy, you can save, factor of 8 or 16 or so in the runtime, which translates to a factor of power, of energy rather, power integrated over time. The last note is coding to the architecture. This is, of course, very intuitive. This is part of the enthroned concept of libraries. But how do we make these GPUs and mics sing? We need to use a lot of tiling and recursive subdivision to create large numbers of small problems that have sufficient uniformity and take advantage of various hardware tricks like non-temporal stores, skipping polluting intermediate levels of cache for data we won't need to read again for a while, coalescing memory accesses, doing double buffering, all to reduce sensitivity to memory latency. The code is much more complex. Only a few people should do this, and it's very architecture specific at the bottom. Where do the cycles go? Dominant consumers in the DOE's supercomputers. A lot of linear algebra on dense symmetric or Hermitian matrices. Hamiltonians in chemistry, maybe a quarter of all DOE cycles in open science. Hessians in optimization. Sure complements in linear elasticity after you've done static condensation. The sparse matrix produces dense symmetric blocks. Covariance matrices in statistics, spatial statistics. People want to go to tens of thousands, hundreds of thousands of points, especially in geospatial. The other big bottleneck is often Poisson solves. It's often the highest order operator in the PDE modeling areas at the bottom. My group, these are just some theses that have recently been written. Every one of these students has to say which of these 4 things are they working on, which of these 4 algorithmic imperatives are they trying to improve. So let me just end with a few examples. If my time runs out, you have extra slides at the end. Let's talk about that expensive eigensolver, or SVD, for instance, quantum chemistry. Recently, Nick Hyam, the current president of SIAM, proposed an algorithm that does an order of magnitude more flops than the best method in Scalapack, but actually, on the right hardware, finishes faster. I'll actually, spend a few slides on that one. KBLAS is a library that we've been developing locally to fill in some holes in L2 BLAS, especially the memory bandwidth limited matrix vector operations for GPUs and mics, but even some L3 BLAS for the symmetric solvers are not optimally implemented in the libraries that the vendors will give you. Balancing domain decomposition with constraints is a linear preconditioner that does a lot of extra flops on interfaces between subdomains. In fact, it does an eigensolver and a Cholesky decomposition within that on each interface. So it's polynomial in a small degree, a small parameter, but it gives you a low condition number to reduce the number of synchronizations for your Krylov method, even in high contrast elliptic problems like reservoir models. Fast multipole, as a solver, often can't compete with multigrid. The multipole expansion has to be rather high. But if you cut it way down, it becomes a competitive preconditioner when coupled with the right boundary conditions. Cyclic reduction is a 52-year-old algorithm that Gene Golub and company introduced, which, if you have constant coefficients, is an n log n method. But if you have variable coefficients, it swells to n squared. But you can reduce it down to n log n, or n log squared n, by compressing those Schur complements with hierarchical matrices. There's a nonlinear preconditioner that will reduce the global synchronizations and replace them with a lot of local synchronizations, little Newton problems on subdomains that lead to a better posed global Newton problem that converges very quickly. And an example of this NEC box, the NEC 5000 code of Fisher, stripped down to a geometrically more simple set of functions for optimization tests on, for example, the incompressible Navier-Stokes results that I just showed you to explore the benefits of very high order. So QDWH, the so-called QR-based dynamically weighted Haley iteration, this is a way of forming a polar decomposition for a dense matrix. And it can be the basis for an eigen or a singular value decomposition. It can be implemented with a DAG-based data flow using tiles, reducing synchrony, increasing the SIMT style concurrency through recursive subdivision of the problems, and it can employ a runtime system. This is how it basically works. You have your general matrix A, which can be factored into a symmetric positive definite matrix and an orthogonal matrix. And then the symmetric positive definite matrix can be subject to a standard eigendecomposition, and then you can form the factors of your SVD, for example, by just multiplying those two together. It can be implemented in a recursive divide and conquer manner. It's backward stable. It's based on vendor-optimized kernels. And the complexity can be much higher than the standard LAPACK method, but these graphs show large factors of improvement based on samples of ill-conditioned or well-conditioned matrices. This is matrix problem size. You can see it's getting into the millions of problem size. Logarithmic time is up, so lower is better. This is actually, I think, the fastest dense SVD known today, and Cray is actually implementing it currently into libsci. This is an example on 1152 nodes of a 32-core Haswell system. Let's see. This is an example showing how the idle regions in the classical algorithm are squeezed out by going to a task-based decomposition. Jack will show you a lot more of these pictures. Again, taskified with a combination of Haswell's and NVIDIA K80s, compared over a variety of different hardware environments. Low-rank Cholesky, this is part of the K-BLAS. This is actually not using the full H-matrix hierarchy, just making a uniform tiling and looking for low-rank replacements of the appropriate tiles. This is a very simple way to retrofit a standard tile-based solver. It comes up, the need of it comes up in a lot of geospatial statistics problems where you have to evaluate this function over and over again, where theta is a vector of parameters to be fit by minimizing this log likelihood. Z is a vector of observations, and sigma is a large, dense covariance matrix, which needs both to be inverted and to have its logarithm, its determinant taken. That's the log of the determinant is the right-handmost term, which can be obtained from the factors of the Cholesky matrix. So here are just some examples of some points where you know data in red and where you want to infer data in the stars, and taken from a real example in the Mississippi basement for moisture, soil moisture. The classic algorithm is not very amenable to concurrency. You have a panel that's good for BLAS3, and it walks across, but the amount of concurrency recursively disappears. This has been solved by tiling and the replacement of those predetermined loops with a DAG. And then those tiles can in turn be replaced with low-rank replacements. And they could be adaptive in the sense that as you get further from the diagonal, the ranks can be smaller, or for thread uniformity in a forest of GPUs, you could say, hey, let's just fix the rank, live with whatever accuracy we get. Perhaps we can just use it as a preconditioner. And this is an example of a synthetic covariance matrix of size 16384, broken up into 16 by 16 blocks of 1K each. And these are 4 typical blocks as you go off the diagonal. And this is a distribution of their singular values from order 1 to machine epsilon. And you see that the diagonal block needs full rank, but the off-diagonal blocks are surprisingly compressible. This is typical of any type of phenomena where there's decay with distance. And this is a comparison of the tile low rank in blue. Again, time is up, so lower is better, versus the MKL or the plasma implementation in full rank. So there's like an order of magnitude improvement in running time with very little compromise of accuracy. Here's an example of a distributed memory implementation of this TLR Cholesky. The K-BLAs are an extension of some vendor BLAs where we found that their original releases weren't optimal in terms of especially BLAS 2. And it's a way of going to batched algorithms by recursive subdivision. So for instance, take TRSM, where you have a triangular, symmetric lower factor. You can break that into 2 smaller triangular lower factors with a big fat dgem in the middle, and you can then recursively go after those triangles until you get something that's small enough to fit on a single core's worth of memory, and batch them up. Here are examples of the out-of-place KUBLAs. The OOP is out of place. It needs twice as much memory. Our K-BLAs is in place, uses half the amount of memory, and gives the same performance. This time, flops is up, so up is good, and it's arithmetically equivalent, so it's equivalent to measuring reciprocal time. The comparable KUBLAs in place was about 5.5 times slower. The green curve is dgem, which is more or less an effective peak of obtainable flops, and the dashed curve is theoretical peak for this particular device. And here's another of the examples. I won't go into all of these, but these are already part of the KUBLAs. And now they're being extended to batched operations. Jack is running a series of workshops on how to create the naming conventions for the BLAS library for GPUs and PHYs and so forth, where we sort of parallelize across the warps with uniform operations. And again, recursively subdivide until you get enough of those little blocks. And here are some examples comparing KUBLAs and the K-BLAs, and Magma, one of the other DAG-based implementations, and MKL. And here up is good, and it's not monotonic, but on both the K40 single and the K40 multiple. Notice the rather linear scaling as you go from 1 to 2 to 4 to 8 log scale in the performance. So it distributes pretty well. And it lives pretty close to the roof line. These are memory bandwidth limited, but they live pretty close to the roof line. So I'm going too fast for full appreciation, but I'm just trying to give you the flavor. We've looked at a few of the components, the white ones, in a group of routines that we're calling the HICMA library, Hierarchical Computation for Many Core Architectures. It's the Arabic word for wisdom. And the gray parts are already well done, and we're not touching them, but some of the replacement of the standard BLAS with hierarchical BLAS, and then the layering of some of the new algorithms based on DAGs or compression above them is what is being targeted here. I will, for those of you, and I know there are a few of you who are very math-oriented here, just to, it's not all computer science, exascale. Exascale means, solving the same problem more cleverly. So here is a set of diffusion coefficients in a reservoir. This is the color scale is log-based. So there's like 7 or 8 orders of magnitude of variation of diffusive coefficient in this problem. Stefano Zampini has been, doing these on, up to, like, say, 50 million degrees of freedom here, using the right, finite elements for Darcy flow. And basically, this is a parameter that targets the condition number of the global preconditioner. And you see the number of iterations is independent of the weak scaling problem size, and the actual condition numbers achieved are very close, in the circles on the right, are very close to the targeted condition numbers. You pick how strong you want your preconditioner to be a priori. You do all the flops on the interface. There's a very expensive upfront cost to store all the factors, and then the individual iterations sail through and are very few. The same thing has been extended to Maxwell in conjunction with Paniot Vasilevsky and the exascale project SEED at Lawrence Livermore, again with the correct H-curl elements, and you see that the targeted condition numbers are achieved. And this satisfies three of the pillars of exascale algorithms: reducing synchronization, increasing arithmetic intensity, and increasing the concurrency of the preconditioning step. And this is now distributed in PETSI, by the way. And I'll skip the derivation of the Schur complement and the equivalent preconditioning block by block. And I'll mention that compression has also been implemented here to reduce the cost of those Choleskis. And there's a heat map showing the accuracy as a function of the tile size for uniform diffusivity and for this Society of Petroleum Engineers benchmark with the 7 or so orders of magnitude of variation. So we have in network science the idea of an hourglass, many applications, many architectures, and the same internet protocol has to serve them all. I think that's a good philosophy for our algorithmic infrastructure. I believe that complex PDE codes will adapt. I'm optimistic about this. The programming model will still be dominantly message passing. That's our code base. But it will be adapted to multi-core and hybrid processors within a relaxed synchronization MPI-like interface. Load balance blocks that we scheduled today with nested loops will be separated into critical and non-critical parts by the programmer. The critical parts will be scheduled with DAGs. The non-critical parts will be made available for NUMA-aware harvesting. We will need to develop greater expressiveness in our scientific programming, creating threads for logically separate tasks, scheduling them with priorities, much like the way an OS works. Join the priority threads in a DAG, and steelwork. If you look at a typical inner loop of a nonlinear implicit PDE solve, you have a linear solve, a bound of a Newton step, and an update. But we often insert many other things into that critical path because of our artifactual way of thinking. We put the Jacobian computation on the critical path. Why? That could be going on to refresh the Jacobian in idle places. We convergence test every time. Why? We could machine learn when we need to convergence test and so forth. This conquering of non-uniformity will not only aid the hardware unreliability of exascale, but it will aid the load balancing struggles that we have today with adaptive algorithms, because it all looks the same when you get to a synchronization point. So there's plenty of ideas. Here are the 4 things you should think about for your application or your tool. Don't be afraid to stretch the programming model or the runtime. Everything should be on the table for trades beyond what your own discipline is used to thinking about. This is what, after all, co-design is about. And so I want to thank you very much for your very kind attention. And I don't want to take much of Cleve's time, so yeah. I see. Oh, yes.
Do you see a future for compilers in this exascale area?
Well, John Mellor-Crummy was here a couple of days ago, right? I think compilers have already started to incorporate various, knowledge about actual specific applications, right? You run a code, it dumps out certain things, compilers look at them, and they retune, their inner optimizations. There's undoubtedly a large amount to be done there, but not, sort of perfect compiler-based parallelism at the large scale. Maybe within a certain restricted number of cores on a node. That's somebody else's a big problem. But I mean, I recognize that there are additional solutions when we merge machine learning with it. But good question, one that I'm not able to answer. I see that Paul Fisher came into the room while we were here. Paul is the one who is responsible for that, the original NEC 5000 code, which has been very ahead of its time, one could say, in exploring high order before the architectures required it.